Listening practice forward the evolution of wastewater treatment. From basic sanitation to resource recovery, wastewater treatment has undergone a transformative journey from rudimentary sanitation practices in ancient civilizations to today's cutting-edge technologies that reclaim water, energy, and nutrients. This book arrives at a pivotal moment, as the global community faces unprecedented water scarcity, pollution, and climate change impacts. Historical milestones, ancient innovations, Roman aqueducts and Mesopotamian drainage systems laid the groundwork for organized sanitation. Industrial revolution, the advent of centralized sewage systems and biological treatment, e.g., activated sludge, 1914. 21st century paradigm shift, transition from waste disposal to resource recovery, driven by circular economy principles. Modern challenges, contaminants of emerging concern, CECs, pharmaceuticals, microplastics, and PFAS demand advanced remediation. Climate resilience, flood-prone infrastructure and energy-intensive processes require sustainable redesign. Equity gaps, 2.2 billion people still lack safely managed drinking water, WHO, 2022. The promise of advanced treatment, technology leap, membrane bioreactors, MBRs, advanced oxidation processes, AOPs, and AI-driven systems enable precision treatment. Resource recovery, wastewater is no longer a liability but a source of clean water, biogas, and fertilizers, e.g., struvite extraction. Global case studies, Singapore's NE Water, closed-loop water reuse via reverse osmosis and UV disinfection. Orange County GWRS, largest potable reuse project, producing 100 million gallons/day. This book equips readers to navigate this evolution, offering tools to design systems that are not only efficient but regenerative. Preface, scope and objectives. This book provides a comprehensive exploration of advanced wastewater treatment technologies, bridging theory, practice, and policy. It addresses 1. Innovative processes, membrane systems, AOPs, biofilm reactors, and nutrient recovery. 2. Contaminant-specific solutions, removal of heavy metals, PFAS, and antibiotic-resistant genes. 3. Sustainability integration, life cycle assessment, LCA, zero liquid discharge, ZLD, and circular water management. Target audience, engineers and operators, practical guidance on designing and optimizing advanced systems, e.g., MBRs, anaerobic digesters. Researchers, deep dives into emerging fields like nanotechnology, microbial fuel cells, and AI-driven process control. Policymakers, frameworks for regulating CECs and incentivizing resource recovery. Unique features, interdisciplinary approach, merges chemical, biological, and environmental engineering with data science. Global perspectives, case studies from Europe's stringent EU Water Framework Directive to decentralized systems in water-stressed regions. Tools for implementation, regulatory compliance checklists, EPA, ISO. Sample designs for hybrid treatment trains. Cost-benefit analyses for energy recovery projects. How to use this book, Academia, a textbook for graduate courses in environmental engineering. Industry, a reference for upgrading treatment plants or tackling industrial effluent. Policy, a primer on balancing innovation with public health safeguards. Acknowledgements. We extend gratitude to the pioneers whose breakthroughs transformed wastewater from a problem to a solution and to the communities worldwide proving that sustainable water management is achievable. This forward and preface frame the book as both a technical guide and a call to action, urging readers to rethink wastewater as a cornerstone of global sustainability. Would you like to refine the focus on specific technologies or regions? Chapter 1, Introduction to Wastewater Treatment. 1.1 Global Water Crisis and the Need for Advanced Treatment. The global water crisis is a pressing challenge, with 2.2 billion people lacking access to safe drinking water, WHO/UNICEF, 2023, and 80% of wastewater discharged untreated into ecosystems, UN Water, 2021. Drivers include population growth and urbanization. Megacities strain aging infrastructure, leading to sewage overflows. Industrialization. Toxic effluents from manufacturing, mining, and chemical industries overwhelm conventional treatment systems. Climate change. Droughts reduce water availability, while floods overwhelm treatment plants. Limitations of conventional systems. Fail to remove contaminants of emerging concern, CECs, like microplastics, pharmaceuticals, and PFAS. Energy-intensive processes exacerbate carbon footprints. Advanced treatment solutions, precision technologies, membrane bioreactors, MBRs, advanced oxidation processes, AOPs. Resource recovery, extracting energy, biogas, nutrients, struvite, and reusable water. 1.2 Types of wastewater, municipal, industrial, and agricultural wastewater type sources. Key characteristics. Treatment challenges. Municipal households, commercial areas. High organic load, pathogens, microplastics. Pharmaceutical residues, aging infrastructure. Industrial factories, refineries. Toxic chemicals, heavy metals. Solvents, dyes, variability in effluent composition, recalcitrant compounds. Agricultural farms, livestock operations. Nutrients, N.P., pesticides, antibiotics. Algal blooms. Runoff management, examples, municipal, estrogen analogs from birth control pills disrupting aquatic ecosystems. Industrial, chromium-laced tannery effluent contaminating groundwater in Bangladesh. Agricultural, nitrate runoff from fertilizers causing dead zones in the Gulf of Mexico. 1.3 Key pollutants and their environmental impacts. Pollutant category examples. Environmental impact. Regulatory limits. Nutrients. Nitrogen, phosphorus. Eutrophication, algal blooms, hypoxia. EPA, 10 mg/L, TN, 0.1 mg/L, TP, pathogens. E. coli, Vibrio cholerae. Waterborne diseases, cholera, dysentery, WHO, 0 CFU/100 ml. Drinking water, organic matter. BOD, cod. Oxygen depletion, fish kills. EU, 25 mg/L. BOD, urban wastewater, heavy metals. Lead, mercury, arsenic. Bioaccumulation, neurological damage. WHO, 0.01 mg/L, as in drinking water. Emerging contaminants. PFAS, microplastics. Endocrine disruption, carcinogenicity. EU, 0.1 g/L, PFAS in drinking water. Case studies, Chesapeake Bay, USA. Nutrient runoff caused a 5,500 square kilometers dead zone, prompting stricter EPA total maximum daily load. TMDL, regulations. Ganges River, India. Pathogen-laden sewage contributes to 500,000 annual child diarrheal deaths. Need for advanced treatment, targeted removal, adsorbents for heavy metals, ozonation for pathogens. Policy alignment, compliance with EU Water Framework Directive, U.S. Clean Water Act. Key takeaways. 1. Global water scarcity and pollution demand innovative wastewater solutions that go beyond conventional methods. 2. Tailored approaches are essential for municipal, industrial, and agricultural wastewater due to distinct pollutant profiles. 3. Emerging contaminants require advanced technologies to mitigate long-term ecological and public health risks. This chapter sets the stage for understanding the urgency and complexity of modern wastewater challenges, framing the need for the advanced technologies explored in subsequent chapters. Chapter 2. Regulatory Frameworks and Standards. 2.1 International Guidelines, WHO, EU Water Framework Directive, World Health Organization, WHO, role, establishes global benchmarks for safe drinking water and wastewater management. Key guidelines, guidelines for drinking water quality, sets thresholds for pathogens, e.g., 0 *E. coli/100 ml, and chemicals, e.g., arsenic less than or equal to 10 g/L. Sanitation safety planning *, Risk management frameworks for wastewater reuse in agriculture. EU Water Framework Directive, WFD, objective, achieve good ecological status for all EU water bodies by 2027. Mechanisms, priority substances list, regulates 45 pollutants, e.g., mercury, PFAS, requiring phased elimination. River basin management plans, tailored strategies for transboundary water systems, e.g., Danube River. UN Sustainable Development Goals, SDGs, SDG 6, targets universal access to safe water and sanitation by 2030, emphasizing wastewater treatment and reuse. 2.2 National Standards, EPA, ISO, United States Environmental Protection Agency, EPA, Clean Water Act, CWA, regulates discharge of pollutants via the National Pollutant Discharge Elimination System, NPDES. Sets effluent limits for industrial sectors, e.g., oil refineries, textiles. Safe Drinking Water Act, SDWA, enforces maximum contaminant levels, MCLs, for 90-plus contaminants, e.g., lead, nitrates. International Organization for Standardization, ISO, ISO 14000 series, standards for environmental management systems, e.g., ISO 14001 for wastewater treatment plants. ISO 30500, guidelines for non-sewered sanitation systems, critical for decentralized solutions. Examples of national adaptation: India uses WHO guidelines but sets stricter limits for arsenic, 10G/L 5G/L, in groundwater-dependent regions. Japan integrates ISO standards with national protocols for industrial effluent, e.g., tetraethyl lead limits. 2.3 Emerging Policies for Contaminants of Emerging Concern, CECs, definition of CECs, pharmaceuticals, microplastics, PFAS, and endocrine disruptors not traditionally regulated but posing ecological/health risks. Recent regulatory advances: EU's watch list monitors CECs like antibiotics, erythromycin, and pesticides, clothianidin, for future regulation. EPA PFAS Action Plan aims to classify PFOA/PFOS as hazardous substances and set MCLs for drinking water. California's microplastics policy, first U.S. state to require monitoring of microplastics in drinking water, 2022. Challenges in regulation: data gaps, limited toxicity studies for thousands of unregulated CECs. Rapid innovation, policies struggle to keep pace with new contaminants, e.g., nanoplastics. Policy approaches: precautionary principle, bans/prohibitions without full evidence, e.g., EU's REACH restrictions on PFAS. Risk-based, cost-benefit analysis for phased regulation, e.g., EPA's unregulated contaminant monitoring rule. Comparative table, key standards for wastewater parameter WHO EU WFD EPA, USA, ISO-arsenic, drinking water, 10G/L 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 N/A-BOD, effluent, not specified 25 mg/L 30 mg/L ISO 5815, test method, PFAS, drinking water, no guideline 0.1 g/L, sum, proposed 4 ng/L N/A. Key takeaways: 1. Global harmonization: WHO and ISO provide foundational guidelines, adapted nationally, e.g., EPA, EU WFD. 2. CEC challenges: emerging policies balance precautionary bans, EU, with risk-based monitoring, EPA. 3. Impact on innovation: regulations drive R&D in advanced treatment, e.g., PFAS removal technologies. Implications for stakeholders: engineers, design systems compliant with evolving standards, e.g., integrating PFAS filtration. Policymakers, foster collaboration between nations to address transboundary pollutants. Researchers, Prioritize data generation on CEC toxicity to inform future regulations. This chapter underscores the dynamic interplay between regulation and technology, emphasizing adaptive frameworks to safeguard water resources in a rapidly changing world. Chapter 3, Conventional Treatment Processes, A Primer 3.1 Primary Treatment, Screening, Sedimentation, Purpose, Remove large solids and settleable organic/inorganic matter. Key processes, screening, removes debris, e.g., plastics, rags, using bar racks, spacing, 1550 mm, or fine screens, 15 mm. Reduces downstream equipment damage and clogging. Grit removal, settles sand, gravel, and eggshells in aerated or vortex chambers, detention time, 2-5 minutes. Primary sedimentation, gravity settling in clarifiers, detention time, 2-3 hours. Removes 50-70% of suspended solids, TSS, and 25-40% of biochemical oxygen demand, BOD. Design parameters, parameter typical value surface loading rate 2040 m superscript 3 m superscript 2 day sludge volume 0.10.3 l person day TSS removal efficiency 50-70% case study, Chicago's Stickney plant, primary treatment reduces TSS by 60%, preparing wastewater for secondary treatment. 3.2 Secondary treatment, activated sludge, trickling filters, purpose, degrade dissolved organic matter using microbial activity. Key processes, activated sludge, mechanism, aerobic bacteria consume organic matter in aeration tanks, do, 24 mg/L. Design, hydraulic retention time, HRT for 8 hours. Mixed liquor suspended solids, MLSs 2,0004,000 mg/L, efficiency, removes 85-95% of BOD and TSS, variants, sequencing batch reactors, SBRs, extended aeration. Trickling filters, mechanism, biofilm on media, plastic, gravel, oxidizes organic matter. Design, organic loading rate, 0.10.4 kg BOD/m superscript 3/day. Recirculation ratio, 1:1 to 4:1. Efficiency, removes 70-85% of BOD. Comparison, parameter activated sludge trickling filters energy use high, aeration, low footprint large compact sensitivity to shock loads moderate high case study, Milwaukee's Jones Island plant. Activated sludge achieves 95% BOD removal, discharging effluent to Lake Michigan. 3.3 Limitations of conventional systems 1. Contaminant removal gaps, nutrients, limited phosphorus, P, and nitrogen, N, removal eutrophication risk. Pathogens, residual bacteria/viruses require tertiary disinfection, e.g., chlorination. Emerging contaminants, pharmaceuticals, microplastics, and PFAS persist. 2 Operational challenges, energy intensity, activated sludge consumes 30-60% of a plant's energy. Sludge management, produces 0.81.2 kg dry sludge/m superscript 3 treated wastewater. Climate sensitivity, cold temperatures reduce microbial activity in trickling filters. 3 Economic and regulatory pressures, cost, high capital and operational expenses for compliance with stricter standards, e.g., EPA's nutrient criteria. Aging infrastructure, many U.S. plants built in the 1970s ADS require costly upgrades. Case study, Chesapeake Bay, conventional plants failed to meet nitrogen limits, necessitating $25 billion in upgrades for BNR, biological nutrient removal. Key takeaways 1. Primary treatment removes solids but leaves dissolved organics. 2. Secondary treatment relies on microbial processes but struggles with nutrients and emerging contaminants. 3. Conventional systems are energy intensive and ill-equipped for modern pollution challenges. Transition to advanced treatment. Limitations of conventional methods set the stage for advanced technologies, e.g., MBRs, AOPs, explored in later chapters. This chapter establishes the baseline for understanding why advanced wastewater treatment is critical in addressing today's environmental and regulatory demands. Chapter 4, Membrane Technology, Precision Separation for Advanced Wastewater Treatment, 4.1 Reverse Osmosis, RO, and Nanofiltration, NF, Principles and Applications, Reverse Osmosis, RO, Mechanism, Semi-permeable membranes, pore size, 0.11 nm, remove dissolved salts, ions, and micropollutants via high pressure, 1570 bar, cross-flow filtration. Applications, desalination, e.g., seawater/brackish water treatment. Removal of PFAS, pharmaceuticals, and nitrates. Efficiency, 95–99% salt rejection. Nanofiltration, NF, mechanism, slightly larger pores, 110 nm, target divalent ions, Ca superscript 2, Mg superscript 2, and organic molecules, 201,000 Da, at lower pressure, 520 bar. Applications, softening hard water. Color and pesticide removal in textile/agricultural effluents. Design parameters. Parameter RONF pore size 0.11 nm 110 nm operating pressure 1570 bar 520 bar energy consumption 310 kWh/m superscript 315 kWh/m superscript 3 typical rejection Na 99%, Cl 99%, Ca superscript 2 90%, dyes 95%. Case studies. Singapore's NE Water, RO polishes treated wastewater for potable reuse, 40% of national demand. Orange County GWRS, RO and UV/advanced oxidation produces 100 million gallons/day of drinking water. Challenges, fouling, scaling, CaCO, silica, and biofouling require antiscalants and CIP, clean in place. Concentrate management, high salinity brine disposal, deep well injection, evaporation ponds. 4.2 Ultrafiltration, UF, and microfiltration, MF, principles and applications. Ultrafiltration, UF, mechanism, pores, 10–100 nm, remove colloids, viruses, and macromolecules, proteins, polysaccharides. Applications, pre-treatment for RO/NF. Tertiary treatment for pathogen removal. Microfiltration, MF, mechanism, larger pores, 0.110 μm, filter bacteria, suspended solids, and turbidity. Applications, clarification of municipal wastewater. Oil/water separation in industrial effluents. Membrane configurations, hollow fiber, high packing density, e.g., submerged MBRs. Spiral wound, compact modules for high-flow systems. Design parameters. Parameter UFMF pore size 10–100 nm 0.110 μm operating pressure 15 bar 0.52 bar flux rate 2100 lmh 5200 lmh typical removal viruses 99.9%, bacteria 99.9%, case studies, Suez ozone biofilter, France UF ensures pathogen-free effluent for river discharge. Toyota's industrial water recycling, MF treats paint shop wastewater for reuse. Challenges, membrane fouling, managed via backwashing, air scouring, and chemical cleaning. Cost, higher capex than conventional sand filters but lower life cycle costs. 4.3 Membrane bioreactors, MBRs, and hybrid systems principles and applications. Membrane bioreactors, MBRs, mechanism, combines activated sludge with UF/MF membranes, pore size, 0.01–0.4 μm, to separate biomass from treated water. Advantages, high quality effluent, TSS 5 mg/L, BOD 5 mg/L. Compact footprint, no secondary clarifiers. Applications: urban wastewater reuse, e.g., irrigation, industrial cooling. High-strength industrial wastewater, food/pharma. Hybrid systems, MBR and RO, produces ultra-pure water for electronics manufacturing. MBR and AOPs, degrades recalcitrant organics, e.g., dyes, pharmaceuticals. Design parameters, parameter value MLS's concentration 8,00012,000 mg/L, flux rate 1530 lmh, aeration energy 0.30.6 kWh/m, superscript 3 membrane lifespan 5-10 years. Case studies: Beijing J. Abadian MBR plant, treats 1 million m superscript 3/day, supporting urban water reuse. Hybrid MBR-RO in Saudi Arabia, recycles oil refinery wastewater for boiler feed. Challenges: energy demand, aeration for fouling control accounts for 50-70% of operational costs. Membrane replacement, costs 20% of annual OPEX. Future trends: anaerobic MBRs, energy-positive systems with biogas recovery. AI-optimized fouling control, predictive maintenance via machine learning. Key takeaways: 1. RO/NF, ideal for desalination and micropollutant removal but require high energy and fouling management. 2. UF/MF, effective for pathogen and particle removal, often paired with advanced processes. 3. MBRs, revolutionize wastewater reuse with compact, high-efficiency systems. 4. Hybrid systems, combine membranes with oxidation or biological processes for tailored solutions. Integration with sustainability goals, membranes enable water reuse, reducing freshwater extraction and supporting circular economies. Emerging materials, e.g., graphene oxide membranes, promise lower energy and fouling resistance. This chapter equips engineers to select, design, and optimize membrane systems for diverse wastewater challenges, balancing performance, cost, and sustainability. LMH equals liters per square meter per hour. Chapter 5, Adsorption and Ion Exchange, Targeted Removal of Contaminants for Clean Water Solutions. 5.1 Activated Carbon and Biochar Applications, Mechanisms and Sources. Activated carbon, production, derived from carbon-rich materials, coal, coconut shells, wood, via pyrolysis and activation. Structure: high surface area, 501,500 m superscript 2/g, with micro and mesopores for adsorbing organic pollutants, e.g., dyes, pharmaceuticals. Biochar, production, pyrolysis of agricultural waste, rice husks, manure, at 400-700 degrees C. Advantages: low cost, sustainable and effective for heavy metals, e.g., Pb superscript 2, Cd superscript 2, due to oxygen-rich functional groups. Applications: municipal water treatment, removes chlorine, pesticides and PFAS, e.g., GAC filters in urban plants. Industrial effluents, treats textile dyes, e.g., methylene blue, with 90% removal efficiency. Soil remediation, biochar immobilizes heavy metals in contaminated soils. Challenges: regeneration, thermal reactivation, 800 degrees Celsius, required, consuming 10-15% of initial production energy. Clogging, fouling by organic matter reduces efficacy over time. Case study: New Jersey's Passaic Valley plant, uses granular activated carbon, GAC, to remove PFAS, achieving 99% efficiency. 5.2 Advanced adsorbents, graphene, metal organic frameworks, graphene oxide, GO, properties, ultra-high surface area, 2630 m superscript 2/g, tunable functional groups. Applications: heavy metals, adsorbs Pb superscript 2, capacity, 501,200 mg/g, via electrostatic interactions. Dyes, removes 95% of rhodamine B from textile wastewater. Challenges, high production cost, $100-200/g, and potential ecotoxicity. Metal organic frameworks, MOFs, structure, porous crystalline materials with metal clusters and organic linkers. Applications, CO capture, MIL 101, CR, achieves 2.5 mol/g CO adsorption. Pharmaceuticals, UIO 66 removes 98% of diclofenac from hospital wastewater. Innovations, water-stable MOFs, e.g., ZIF-8, for aqueous environments. Comparative efficiency, adsorbent surface area, M superscript 2/g, pollutant capacity, mg/g, activated carbon 1000 methylene blue 300 graphene oxide 2600 MOF 808 4500 lead, Pb superscript 2, 1200 arsenic, A superscript 3, 200 case study, MIT's MOF-based filters, deployed in Flint, Michigan, to adsorb lead from drinking water. 5.3 Selective ion exchange for heavy metal removal principles, mechanism, swaps target ions, e.g., Cu superscript 2, Hg superscript 2, with benign ions, Na, H, on resin surfaces. Resin types, chelating resins, iminidiacetic acid groups selectively bind transition metals, e.g., porolite S930. Strong acid cation, SAC sulfonic acid groups for general metal removal. Applications, mining effluents, removes 99% of Cu superscript 2 from acid mine drainage. Electroplating wastewater, recovers nickel and chromium for reuse. Regeneration, chemical elution, HCl or H2SO4, 12M, strips metals from resins. Waste management, spent brine treated via precipitation or electrocoagulation. Case study, Chile's Codelco mines, ion exchange reduces copper concentrations from 500 mg/L to 0.1 mg/L. Key takeaways 1. Activated carbon/biochar, cost effective for organic pollutants and heavy metals but face regeneration challenges. 2. Advanced adsorbents, graphene and MOFs offer superior capacity and selectivity but require cost and scalability improvements. 3. Ion exchange, ideal for targeted heavy metal recovery, though brine management is critical. Future directions, hybrid systems, combine biochar with MOFs for enhanced performance. Circular economy, regenerate adsorbents using green solvents, e.g., ionic liquids. This chapter equips practitioners to select adsorption/ion exchange technologies tailored to pollutant profiles, balancing efficiency, cost, and sustainability. Discussion questions. 1. How can biochar production be standardized to ensure consistent adsorption performance? 2. What ethical considerations arise from using nanomaterials like graphene in water treatment? Exercises. 1. Calculate the adsorption capacity of a graphene oxide filter treating lead contaminated water. 2. Design an ion exchange system for a zinc plating facility to achieve 99% metal recovery. Chapter 6, Advanced Oxidation Processes, AOPs, Harnessing Reactive Radicals for Contaminant Destruction, 6.1 Ozonation and UV/hydrogen peroxide systems mechanisms. Ozonation, O generates hydroxyl radicals, O, via ozone decomposition, especially at high pH. \text O_3 plus \text ho \right arrow \text ho _2 plus \text O_2 \right arrow \text O UV/HO, UV light cleaves HO into O radicals. \text H_2 \text O_2 plus \text UV \right arrow 2 \text O combined O/UV/HO, Synergistic radical production enhances degradation of recalcitrant pollutants. Applications: pharmaceutical removal, degrades 90% of antibiotics, e.g., sulfamethoxazole, in hospital wastewater. Taste/odor control, eliminates geosmin and MIB in drinking water. Case studies: Zurich water treatment, Switzerland. Ozone and UV reduces micropollutants by 80% in municipal effluent. Los Angeles GWRS, UV/HO polishes RO permeate for potable reuse. Challenges: bromate formation, ozone reacts with bromide in water, regulated to 10 G/L by WHO. Energy cost: UV systems consume 5100 kWh/million gallons. 6.2 Photocatalysis, TIO, ZNO, principles, mechanism: UV/solar light excites electrons in TIO/ZNO, creating electron hole pairs that generate O. \text TO_2 plus H \new \right arrow E plus H plus \right arrow \text O nanomaterials, nano-TO, 1050 nm, increases surface area and reactivity. Applications: dye degradation, removes 95% of azo dyes, e.g., methyl orange, in textile effluents. Emerging contaminants, breaks down PFAS and endocrine disruptors under solar light. Design parameters: parameter optimal range catalyst loading 0.52 G/L/pH 35, TIO, 79, ZNO, light intensity 2050 MW/cm superscript 2, UVA, innovations, doped catalysts, and doped TIO for visible light activation. Immobilized systems, TIO-coated reactors avoid nanoparticle recovery issues. Case study: solar photocatalysis in India, TIO-coated panels treat pesticide runoff, achieving 85% removal. 6.3 Electrochemical oxidation and plasma treatment. Electrochemical oxidation, mechanism: anodes, e.g., boron-doped diamond, BDD, directly oxidize organics or generate O. \text R \right arrow \text CO_2 plus \text H_2 \text O Applications: landfill leachate, removes 99% cod at 100-200 A/m superscript 2 current density. Heavy metals, electrodeposition of Cu superscript 2, Ni superscript 2 from industrial effluents. Plasma treatment, mechanism: electrical discharge generates reactive species, O, UV photons. Non-thermal plasma, operates at ambient conditions, e.g., dielectric barrier discharge. Applications: pharmaceuticals, degrades 90% of diclofenac in 30 minutes. Pathogen inactivation, achieves 6 log reduction in bacteria. Comparative analysis, parameter electrochemical plasma energy use 1050 kWh/kg cod 520 kWh/m superscript 3 scalability pilot to full-scale lab to pilot scale byproduct risk chlorinated organics NO/O in air case studies, BDD electrodes in Spain, treats olive mill wastewater, reducing cod by 95%. Plasma reactors in Japan, degrades PFAS in groundwater with 80% efficiency. Key takeaways: 1. AOPs excel at destroying complex pollutants, PFAS, drugs, but require energy/chemical inputs. 2. Photocatalysis offers solar-driven solutions but faces catalyst recovery challenges. 3. Electrochemical/plasma systems are chemical-free but need cost reductions for scalability. Future trends: hybrid systems, pair AOPs with adsorption or biologics for cost efficiency. Renewable integration, solar-powered plasma or electrochemical reactors. This chapter equips engineers to deploy AOPs strategically, balancing efficacy, cost, and sustainability for modern water challenges. Discussion questions: 1. How can AOPs be optimized to minimize energy use while maximizing contaminant degradation? 2. What regulatory frameworks are needed to address byproducts like bromate or chlorinated organics? Exercises. 1. Calculate the O yield for a UV/HO system treating 1000 L/HR of wastewater. 2. Design a TiO photocatalysis unit for a textile plant targeting 90% dye removal. Chapter 7, Biological Nutrient Removal, BNR, Harnessing Microbes for Efficient Nutrient Management, 7.1 Enhanced Nitrogen Removal, Anammox, Sharon Process, Traditional Nitrification Denitrification, Process, Ammonia, NH, Nitrite, No, Nitrate, No, Nitrogen gas, N. Limitations, energy intensive, aeration for nitrification, and requires organic carbon for denitrification. Innovative approaches, Sharon process, mechanism, partial nitrification in a single reactor at high temperature, 30-40 degrees C, and pH, 7.5-8.5, favoring ammonia oxidizing bacteria, AOB, over nitrite oxidizing bacteria, NOB. Converts 50% of NH to NO. Benefits, reduces oxygen demand by 25% and eliminates need for organic carbon. Anammox, anaerobic ammonium oxidation, mechanism, Anammox bacteria, e.g., Brocadia, combine NH and NO directly into N-gas under anoxic conditions, reaction, NH and NO N plus 2HO, applications, Demon registered trademark systems integrate Sharon and Anammox for energy-neutral nitrogen removal. Case study, Rotterdam WWTP, Netherlands Demon system achieves 85% nitrogen removal with 60% less energy than conventional methods. 7.2 Phosphorus recovery via EBPR, enhanced biological phosphorus removal, EBPR mechanism, 1 anaerobic phase, PAUS, polyphosphate accumulating organisms, release stored phosphorus, P, and uptake volatile fatty acids, VFAs, as FOS. 2 aerobic phase, PAUS oxidize FOS, taking up 3-5x more P than released, storing it as polyphosphate. 3P removal, phosphorus-rich sludge is wasted, reducing effluent P to 0.5 mg/L. Phosphorus recovery, struvite precipitation, adding Mg superscript 2 to P-rich sludge forms struvite, MgNH-PO6HO, a slow-release fertilizer. Direct extraction, acid leaching of sludge to recover HPO for industrial use. Benefits, reduces eutrophication risk and recycles P, a non-renewable resource. Example, Oster's Pearl registered trademark process recovers 85-90% P as struvite. 7.3 Bioaugmentation and Microbial Consortia. Bioaugmentation, definition, introducing specialized microbes, e.g., Anammox bacteria, PAUS, to enhance treatment efficiency. Applications, accelerating startup of Anammox reactors, inoculation with enriched biomass. Boosting PAU populations in EBPR during low VFA availability. Microbial consortia, synergistic communities, nitrifiers and denitrifiers, complete nitrogen cycle in BNR. PAUs and GAUs, glycogen accumulating organisms compete for VFAs, requiring careful process control. Challenges, competition, indigenous microbes may outcompete introduced strains. Environmental sensitivity, temperature, pH, and DO must align with microbial needs. Innovations, CRISPR-engineered strains, microbes tailored for high P uptake or toxin degradation. Syntrophic consortia, cross-feeding communities, e.g., fermenters and methanogens, for complex waste streams. Key takeaways. 1. Sharon Anammox systems, cut energy use by 60% and carbon demand by 90% versus traditional nitrogen removal. 2. EBPR and struvite recovery, transforms P from pollutant to resource, supporting circular economies. 3. Bioaugmentation, enhances BNR efficiency but requires precise operational control. Future directions, AI-driven microbial management, predictive models to optimize consortia interactions. Decentralized BNR systems, modular reactors for rural/industrial applications. This chapter underscores the role of microbial ingenuity in sustainable wastewater treatment, balancing ecological health with resource recovery. Discussion questions: 1. How can Sharon anammox systems be adapted for colder climates where anammox bacteria grow slowly? 2. What policies could incentivize phosphorus recovery in municipal wastewater plants? Exercises: 1. Calculate the theoretical energy savings of a Sharon anammox system treating 10,000 m superscript 3/day of wastewater. 2. Design a bio-augmentation strategy for a plant struggling with EBPR efficiency due to low VFA availability. Chapter 8, Biofilm and Fixed Film Systems, Enhancing Wastewater Treatment with Attached Microbial Communities, 8.1 Moving Bed Biofilm Reactors, MBBR, Mechanism, utilizes small, buoyant plastic carriers, e.g., polyethylene, that move freely in the reactor, providing surfaces for biofilm growth. Aeration or mechanical mixing ensures carrier movement, maximizing contact between biofilm and wastewater. Advantages: high biomass retention, carriers retain biofilm, preventing washout and enabling higher microbial density. Resilience, handles variable loads and toxic shocks better than suspended systems. Compact design, upgrades existing plants without expanding tank size, e.g., municipal WWTPs in Norway. Challenges: carrier fouling, requires periodic cleaning to prevent clogging. Carrier loss, mitigated by screens or sieves at reactor outlets. Case study: Oslo's VEAS plant, MBBR achieves 95% BOD removal and 80% nitrogen reduction in a limited footprint. 8.2 Integrated Fixed Film Activated Sludge, IFAS, Mechanism, hybrid system combining fixed biofilm carriers, stationary or semi-stationary, with suspended activated sludge. Biofilm supports slow-growing nitrifiers, while suspended sludge degrades organic matter. Advantages: enhanced nutrient removal, simultaneous COD, NH, and P removal, e.g., TP 0.5 mg/L. Retrofitting, easily integrated into existing activated sludge basins. Operational considerations: balance, maintain equilibrium between biofilm and suspended biomass to avoid dominance of one community. Aeration, optimized to support both aerobic biofilm and suspended sludge. Case study: New York's Wards Island WWTP, IFAS meets stringent NH limits, 1 mg/L, in a high-flow urban setting. 8.3 Granular Sludge Technologies, aerobic granules, mechanism, granule formation, self-immobilized microbial aggregates, 0.53 mm, under selective pressure, short settling times, feast-famine feeding. Layered structure, aerobic outer layer, nitrification, COD oxidation. Anoxic/anaerobic core, denitrification, phosphorus uptake. Advantages: compact reactors, single tank nutrient removal, e.g., Nareda registered trademark technology. Low energy, reduced aeration needs due to efficient oxygen diffusion. Challenges: start-up time, 2-3 months to develop mature granules. Stability, requires precise control of organic loading and shear forces. Case study: South Africa's Gansba WWTP, aerobic granules achieve 90% N and P removal in half the footprint of conventional systems. Key takeaways: 1. MBBR, ideal for space-constrained upgrades, offering robustness and ease of integration. 2. IFAS, balances biofilm and suspended growth for stringent nutrient standards. 3. Aerobic granules, emerging technology for compact, energy-efficient treatment with layered microbial activity. Future directions: AI-driven control, optimize biofilm carrier interactions and granule stability. Resource recovery, integrate granular systems with P recovery, e.g., struvite. This chapter highlights biofilm systems as versatile solutions for modern wastewater challenges, emphasizing adaptability, efficiency, and sustainability. Discussion questions: 1. How does carrier geometry in MBBR influence biofilm development and treatment efficiency? 2. What operational strategies prevent granule disintegration in aerobic granular sludge reactors? Exercises: 1. Design an MBBR retrofit plan for a plant needing to double its treatment capacity. 2. Compare the energy consumption of PFAS versus conventional activated sludge for nitrogen removal. Anaerobic digestion and biogas production, a structured overview. 9.1 High-rate anaerobic reactors, UASB, EGSB, definition and mechanism. UASB, upflow anaerobic sludge blanket. Wastewater flows upward through a dense sludge bed where microbial granules degrade organic matter. Methane and CO are collected at the top. EGSB, expanded granular sludge bed similar to UASB but operates at higher upflow velocities, expanding the sludge bed for better mixing and substrate contact, suitable for complex or high-load wastewaters. Key features: granular sludge, dense microbial aggregates, hydrolysis, acidogenesis, acetogenesis, methanogenesis. Microbes, enhance efficiency and retention. Applications: treat industrial wastewater, e.g., food processing, breweries, municipal sewage. Advantages: high organic loading rates, compact design, low energy use, and sludge stability. Challenges: granule maintenance, sensitivity to toxic shocks, temperature control. 9.2 CO digestion of organic waste. Concept: mixing diverse organic wastes, e.g., agricultural residues, manure, food waste, to optimize C/N ratio, nutrient balance, and biogas yield. Benefits: enhanced methane production, synergistic effects increase biogas output by 20 to 50%. Process stability, buffers pH fluctuations and dilutes inhibitors, e.g., ammonia, VFAs. Challenges: logistical feedstock collection, potential inhibition from lipids/toxins, pre-treatment needs. Examples: dairy farm CO digesting manure with crop residues, wastewater plants adding fog, fats, oils, grease, to sludge. 9.3 Biogas upgrading and utilization, upgrading techniques, water/chemical scrubbing, remove CO and HS via absorption. Membrane separation, selective gas permeation under pressure. Pressure swing adsorption, PSA adsorbents capture CO. Cryogenic separation, liquefies CO at low temperatures. Utilization, biomethane, grid injection, vehicle fuel, compressed natural gas. Electricity/heat, combined heat and power, CHP, systems. Environmental impact, reduces GHG emissions by replacing fossil fuels. Economic considerations, high upfront costs for upgrading technologies balanced by renewable energy credits and dig-state fertilizer sales. Interconnections and sustainability, integrated systems, high-rate reactors and CO digestion boost biogas production, which upgrading transforms into versatile energy. Circular economy, waste valorization reduces landfill use, produces renewable energy, and returns nutrients via dig-state. Global applications, UASB in developing nations for low-cost sanitation, EU biogas plants supplying biomethane for transport. Conclusion: advances in reactor design, feedstock diversification, and purification technologies are critical for scalable, sustainable biogas systems, contributing to energy transition and waste management goals. Part 4, Contaminant-specific treatment strategies. 10. Removal of heavy metals and toxic substances. Heavy metals, e.g., lead, cadmium, arsenic, mercury, and toxic substances, e.g., cyanide, persistent organic pollutants, pose significant environmental and health risks. Effective removal strategies combine physicochemical, biological, and advanced technologies. 10.1 Precipitation, coagulation, and flocculation, mechanisms. Precipitation converts soluble metal ions into insoluble solids, e.g., hydroxides, sulfides, carbonates, using agents like NaOH, CaO, or NaS. Example, Pb superscript 2 plus 2O Pb, O. Coagulation neutralizes charged particles using coagulants, e.g., alum, ferric chloride, to destabilize colloidal suspensions. Flocculation aggregates destabilized particles into larger flocks via gentle mixing, enabling sedimentation or filtration. Applications: industrial wastewater, mining, electroplating, battery manufacturing. Remediation of arsenic-contaminated groundwater. Advantages: cost-effective for high metal concentrations. Rapid treatment with established protocols. Challenges: sludge generation requiring safe disposal. Limited efficiency for low concentration or complex mixtures. 10.2 Phytoremediation and biosorption. Phytoremediation, process, plants uptake, sequester, or degrade contaminants. Phytoextraction, hyperaccumulator plants, e.g., Brassica junci for lead, absorb metals into biomass. Phytostabilization, root systems immobilize metals to prevent leaching. Applications: soil/water remediation in mining sites, agricultural lands. Biosorption, mechanism, biomass, algae, fungi, agricultural waste, binds metals via ion exchange, complexation, or adsorption. Example, chitosan, from crustacean shells, adsorb Cu superscript 2, Cr. Applications: low-cost treatment for dilute metal streams. Advantages: eco-friendly, solar-driven, phytoremediation. Renewable biosolvents, e.g., coconut husks, rice husk ash. Challenges: slow process for large-scale remediation. Biomass disposal post-contamination. 10.3 Electrokinetic and electrochemical methods. Electrokinetic remediation, mechanism, electric current induces metal migration, electromigration, electrophoresis, toward oppositely charged electrodes. Applications: soil remediation, e.g., lead, cadmium in clayey soils. Enhancements: pH adjustment or chelating agents, e.g., EDDA, to improve metal mobility. Electrochemical methods, electrodeposition, metal ions reduced and recovered as pure metals on cathodes. Example, Cu superscript 2 plus 2 ECU, S, for copper recovery. Electrooxidation, degrades organic toxins, e.g., cyanide, using reactive oxygen species, O, at anodes. Advantages: high selectivity and recovery of valuable metals. Minimal chemical additives. Challenges: high energy consumption. Electrode fouling and maintenance costs. Interconnections and sustainability, hybrid systems, combining methods, e.g., precipitation and biosorption, enhances efficiency for mixed contaminants. Circular economy, recovered metals, e.g., Cu, Ni, can be reused in industries, phytoremediation biomass converted to bioenergy. Emerging trends, nanomaterials, e.g., iron nanoparticles, for enhanced adsorption. Genetic engineering of hyperaccumulator plants for faster remediation. Conclusion: tailoring treatment strategies to contaminant type, concentration, and site conditions ensures cost-effective and sustainable remediation. Advances in material science and biotechnology are critical for addressing complex pollution scenarios. Part 4, Contaminant-specific treatment strategies 11. Treatment of persistent organic pollutants, POPs. Persistent organic pollutants, POPs, resist degradation, posing long-term environmental and health risks. This section explores strategies for mitigating pharmaceuticals, PFAS, pesticides, and microplastics. 11.1 Degradation of pharmaceuticals and personal care products. PPCPs, mechanisms, advanced oxidation processes, AOPs generate hydroxyl radicals, O, via ozone/UV, UV/HO, or Fenton reactions to break down complex molecules. Adsorption, activated carbon or biochar captures PPCPs, effective for lipophilic compounds. Biological treatment, engineered bacteria or enzymes, e.g., LACCases, degrade contaminants in bioreactors. Membrane filtration, nanofiltration/reverse osmosis physically removes PPCPs. Applications, wastewater treatment plants supplementing traditional methods with ozonation. Hospital effluent treatment using AOPs to target antibiotics. Advantages, AOPs achieve high degradation rates for diverse PPCPs, biological methods are low energy and scalable. Challenges, AOPs are energy intensive and may produce toxic byproducts. Membrane fouling and adsorbent regeneration costs. 11.2 PFAS, per and polyfluoroalkyl substances, remediation, mechanisms, adsorption, granular activated carbon, GAC, or ion exchange resins trap PFAS, favored for long-chain compounds. Destruction technologies, high-temperature incineration, plasma reactors, or supercritical water oxidation break CF bonds. Electrochemical methods, reductive defluorination using catalysts to degrade PFAS into harmless ions. Applications, groundwater remediation using GAC in firefighting foam-impacted sites. Pilot-scale electrochemical reactors treating industrial wastewater. Advantages, ion exchange offers high selectivity for short-chain PFAS. Emerging destruction methods minimize secondary waste. Challenges, high energy costs for thermal/electrochemical techniques. Limited efficacy of GAC for short-chain PFAS and regeneration issues. 11.3 Pesticide and microplastic removal, pesticides, chemical oxidation, AOPs degrade pesticides like atrazine into less toxic compounds. Phytoremediation, plants, e.g., sunflowers, uptake and metabolize pesticides in soil/water. Coagulation flocculation, alum/ferric chloride aggregates pesticides for sedimentation. Microplastics, physical removal, membrane bioreactors, MBRs, or electrostatic separation capture particles. Coagulation, aluminum-based coagulants cluster microplastics for filtration. Biodegradation, enzymes, PETase, or bacteria break down specific polymers, e.g., polyethylene. Applications, agricultural runoff treatment via constructed wetlands. Urban wastewater plants integrating MBRs for microplastic removal. Advantages, coagulation is cost-effective for large-scale microplastic removal. Enzymatic degradation offers targeted polymer breakdown. Challenges, pesticide degradation may yield toxic intermediates. Microplastic diversity complicates universal solutions. Interconnections and sustainability, hybrid systems, AOPs paired with biological treatment reduce energy use for PPCPs, coupling GAC adsorption with electrochemical destruction addresses PFAS waste. Circular economy, recovered metals from electrochemical PFAS treatment reused in industries. Microplastic-laden sludge repurposed in construction materials. Emerging trends, biochar functionalized with nanoparticles for enhanced adsorption. CRISPR-engineered microbes for targeted pesticide degradation. Conclusion, effective POPs treatment requires tailored, integrated approaches. Innovations in catalytic materials, biotechnology, and policy frameworks are vital to balance efficacy, cost, and sustainability. Addressing transformation products and secondary waste remains critical for holistic environmental protection. Part 4, Contaminant-specific treatment strategies 12. Disinfection and microbial control. Disinfection and microbial control are critical to prevent waterborne diseases and combat antibiotic resistance. This section explores advanced methods for pathogen removal and mitigating antibiotic resistance genes, ARGs. 12.1 Advanced disinfection methods, UV LED, ozone, mechanisms. UV LED uses light-emitting diodes emitting ultraviolet, UVC, light to damage microbial DNA/RNA, preventing replication. Operates at specific wavelengths, e.g., 265-275 nm, with adjustable intensity. Ozone, O is strong oxidizer generated via corona discharge or UV irradiation. Destroys pathogens by oxidizing cell membranes and nucleic acids. Applications: municipal water treatment plants integrating UV LED for energy-efficient disinfection. Ozone in hospitals for surface sterilization and in food processing to eliminate pathogens. Advantages: UV LED, mercury-free, compact, and longer lifespan compared to traditional UV lamps. Ozone, rapid action, no residual chemicals, effective against viruses and chlorine-resistant parasites, e.g., Cryptosporidium. Challenges: UV LED, lower penetration depth in turbid water, higher initial costs. Ozone, forms harmful byproducts, e.g., bromate, in bromide-rich water, requires on-site generation. 12.2 Membrane distillation for pathogen removal, mechanism, thermal-driven process where heated feedwater vapor passes through a hydrophobic membrane, leaving non-volatile pathogens, bacteria, viruses, and salts in the retentate. Applications: desalination of brackish water in remote areas. Treating industrial wastewater with high pathogen loads, e.g., pharmaceutical effluents. Advantages: near complete removal of pathogens and micropollutants. Operates at lower temperatures, 50-80 degrees C, compared to conventional distillation. Challenges: membrane fouling from organic matter, high energy demand for heating. Limited scalability due to cost and maintenance requirements. 12.3 Antibiotic resistance genes, ARGs, mitigation, mechanisms, advanced oxidation processes, AOPs, hydroxyl radicals degrade extracellular DNA carrying ARGs. Membrane filtration, physically removes ARG hosting bacteria via ultrafiltration/nanofiltration. Bioelectrochemical systems, use microbial activity to degrade ARGs in wastewater. Applications: hospital wastewater treatment to reduce ARG discharge. Agricultural runoff management to limit ARG spread from livestock. Advantages: AOPs target both free ARGs and antibiotic residues. Membrane filtration provides a physical barrier against bacterial transmission. Challenges: incomplete degradation of intracellular ARGs within surviving bacteria. Risk of horizontal gene transfer if treatment is partial. Interconnections and sustainability, hybrid systems, combining UV LED with ozone enhances disinfection synergy while reducing chemical use. Integrating membrane distillation with AOPs addresses both pathogens and ARGs in a single process. Circular economy, recovered heat from membrane distillation reused for preheating feedwater. Ozone byproducts, e.g., oxygen, repurposed for aerobic biological treatment. Emerging trends, solar-driven UV LED systems for off-grid water disinfection. CRISPR-based technologies to selectively disrupt ARGs in wastewater. Conclusion: advanced disinfection methods and ARG mitigation strategies are essential to safeguard public health and ecosystems. Innovations in energy-efficient technologies, e.g., UV LED, hybrid systems, and genetic tools will drive sustainable solutions. Addressing operational costs, byproduct risks, and scalability remains pivotal for global implementation. Part V, Sludge Management and Resource Recovery 13. Advanced sludge treatment. Sludge treatment is critical for reducing waste volume, recovering resources, and minimizing environmental impacts. Advanced methods focus on energy recovery, volume reduction, and safe disposal or reuse. 13.1 Thermal hydrolysis and anaerobic digestion. Thermal hydrolysis, mechanism, sludge is heated, 150-170 degrees C, under high pressure to break down complex organic polymers, proteins, cellulose, enhancing biodegradability. Applications: pre-treatment for anaerobic digestion, sewage sludge from municipal/industrial plants. Advantages: increases biogas yield by 20–50%. Reduces viscosity for easier dewatering. Challenges: high energy input, corrosion risks in reactors. Anaerobic digestion mechanism: microbial decomposition of hydrolyzed sludge produces biogas, CO, and stabilized dig state. Applications: CO digestion with food waste or fats to boost methane production. Advantages: renewable energy generation, biogas for heat/electricity. Dig state can be used as fertilizer. Challenges: sensitivity to pH, temperature, and toxic inhibitors, e.g., ammonia. 13.2 Pyrolysis and gasification for energy recovery. Pyrolysis mechanism: thermal decomposition of dried sludge at 300–800 degrees C in oxygen-free conditions produces biochar, syngas, and bio-oil. Applications: energy recovery from sewage sludge, hazardous waste treatment. Advantages: biochar for soil amendment or carbon sequestration. Syngas, CO, H, usable for heat/power. Challenges: high moisture content requires pre-drying, tar formation. Gasification mechanism: partial oxidation at 700–1200 degrees C converts sludge into syngas, CO, H, CH, and inert slag. Applications: large-scale sludge-to-energy plants. Advantages: higher energy efficiency than incineration. Slag can be reused in construction. Challenges: ash management, high capital/operational costs. 13.3 Dewatering and drying technologies, mechanical dewatering, methods, centrifuges, belt presses, or filter presses reduce sludge moisture from 95% to 60–80%. Applications: municipal wastewater plants, industrial sludge. Advantages: lowers transport and disposal costs. Prepares sludge for thermal treatments, e.g., pyrolysis. Challenges: polymer additive costs, fouling of equipment. Thermal drying mechanism: indirect/direct dryers, e.g., rotary, solar, reduce moisture to 10%, producing granular solids. Applications: sludge to fuel processes, agricultural reuse. Advantages: pathogen inactivation, improved calorific value for incineration. Challenges: energy intensive, odor control requirements. Interconnections and sustainability, integrated systems, thermal hydrolysis and anaerobic digestion and dig state drying creates a closed-loop energy recovery system. Pyrolysis/gasification paired with biogas from digestion maximizes energy output. Circular economy, biochar improves soil health and sequesters carbon. Syngas and biogas offset fossil fuel use in wastewater treatment plants. Emerging trends: AI-driven optimization of dewatering and drying processes. Plasma gasification for zero-waste sludge conversion. Conclusion: advanced sludge treatment transforms waste into energy, nutrients, and reusable materials, aligning with circular economy goals. Innovations in thermal processes, dewatering efficiency, and hybrid systems are key to sustainable sludge management. Addressing energy demands and cost barriers will drive broader adoption. Part B: Sludge Management and Resource Recovery. 14. Resource recovery from wastewater. Resource recovery transforms wastewater into valuable products, aligning with circular economy principles. This section explores nutrient, energy, and water recovery strategies. 14.1 Nutrient recovery, struvite, algae-based systems, mechanisms. Struvite precipitation: magnesium and phosphate ions react under alkaline conditions to form struvite, MgNH+6HO, a slow-release fertilizer. Example: Mg superscript 2 and NH and PO superscript 3 Mg NHPO, algae-based systems, microalgae, e.g., chlorella, Cynodesmus, assimilate nitrogen and phosphorus during growth, later harvested for biofertilizers, biofuels, or animal feed. Applications: municipal wastewater plants recovering phosphorus from anaerobic digesters supernatant. Agricultural runoff treatment using algal ponds to capture excess nutrients. Advantages: struvite reduces reliance on mined phosphate, a finite resource. Algae systems sequester CO and produce biomass for multiple uses. Challenges: struvite requires pH control and magnesium addition. Algae harvesting is energy intensive, contamination risks in open ponds. 14.2 Energy harvesting, microbial fuel cells, mechanism, microbial fuel cells, MFCs. Electroactive bacteria oxidize organic matter in wastewater, transferring electrons to an anode. Electrons flow to a cathode, generating electricity. Products: electricity, 0.11 W/m superscript 2, hydrogen, via microbial electrolysis cells. Applications: decentralized wastewater treatment in rural areas. Integration with anaerobic digestion to boost energy recovery. Advantages: simultaneous wastewater treatment and renewable energy production. Low energy input compared to conventional methods. Challenges: low power density limits scalability. Electrode fouling and high material costs for large-scale systems. 14.3 Water reuse and reclamation standards, technologies, advanced filtration, reverse osmosis, RO, ultrafiltration, and nanofiltration remove pathogens and contaminants. Disinfection, UV, ozone, or chlorine ensure microbial safety. AOPs, degrade trace organics, e.g., pharmaceuticals, for potable reuse. Standards, WHO guidelines, focus on microbial and chemical safety for irrigation/industrial use. EPA/EU regulations, define limits for turbidity, TOC, and specific contaminants, e.g., nitrates, in reclaimed water. Applications: industrial cooling, agricultural irrigation, e.g., Israel's wastewater reuse for 85% of irrigation. Direct potable reuse in water-scarce regions, e.g., Singapore's NE water. Advantages: reduces freshwater extraction and pollution discharge. Supports drought resilience and sustainable urban planning. Challenges: public perception of toilet-to-tap systems. High capital costs for advanced treatment infrastructure. Interconnections and sustainability, hybrid systems, algae-based nutrient recovery and MFCs create synergies. Algae provide organic matter for MFCs, MFCs power algae harvesting. Struvite recovery paired with RO concentrates enhances phosphorus removal and water reuse. Circular economy, struvite sold as fertilizer offsets wastewater treatment costs. Reclaimed water for industrial use reduces freshwater demand. Emerging trends, bioelectrochemical systems, combine MFCs with nutrient recovery for multi-resource extraction. Smart sensors, real-time monitoring of water quality to meet reuse standards efficiently. Conclusion: resource recovery from wastewater nutrients, energy, and water turns waste into assets, advancing sustainability and resilience. Scaling these technologies requires innovation in materials, e.g., cost-effective MFC electrodes, policy incentives, and public education. Prioritizing integrated systems and stringent standards ensures safe, equitable resource cycles for future generations. Part 6, Sustainability and Emerging Innovations 15. Life Cycle Assessment, LCA, and Circular Economy. This section evaluates the environmental and economic impacts of water treatment systems while advancing closed-loop resource management. 15.1 Environmental and Economic Trade-offs, LCA Framework, Scope, analyzes environmental impacts, e.g., carbon footprint, eutrophication, energy use, across stages: material extraction, construction, operation, and decommissioning. Tools: software like CymaPro or OpenLCA quantifies impacts using databases, e.g., EcoInvent. Trade-offs: example, anaerobic digestion reduces sludge volume and generates biogas, environmental benefit, but requires energy for thermal hydrolysis, economic cost. Metrics: cost-benefit analysis, CBA, balances capital/operational expenses against pollution reduction and resource recovery. Challenges: data gaps for novel technologies, e.g., PFAS destruction methods. Balancing short-term costs with long-term sustainability gains. 15.20 Liquid discharge, ZLD, systems, mechanisms, thermal processes, multi-effect evaporators and crystallizers recover 95% water as distillate, leaving solid salts. Membrane technologies, reverse osmosis, RO, and electrodialysis concentrate brine for further evaporation. Applications: industries with high salinity wastewater, textiles, coal-fired power plants. Mining operations to recover metals, e.g., lithium, from brine. Advantages: eliminates pollution discharge, complies with stringent regulations. Recovers water and salts for reuse, e.g., NaCl for industrial processes. Challenges: high energy demand, 415 kWh/m superscript 3, capital-intensive infrastructure. Scaling and corrosion in evaporators. 15.3 Circular water management frameworks, principles, closed-loop systems, industrial symbiosis, e.g., a brewery's treated wastewater used for urban irrigation. Policy drivers: EU Circular Economy Action Plan, California's of 1144 promoting water reuse. Case studies: Singapore's NE Water, blends reclaimed water with reservoirs, meeting 40% of water demand. Kalundborg Symbiosis, Denmark Inter-Industry Resource Exchange, e.g., sludge as fertilizer. Challenges: regulatory fragmentation across regions. Public resistance to indirect potable reuse. Interconnections and innovations, integrated systems, ZLD and LCA, optimizes energy use by pairing solar thermal with evaporators. Circular frameworks integrate nutrient recovery, Part V, and water reuse, Section 14.3. Emerging trends, digital twins, simulate LCA outcomes for real-time decision-making. Green chemistry, non-toxic antiscalants for ZLD systems. Blockchain, track water reuse and resource flows in circular networks. Conclusion: transitioning to circular water systems demands holistic LCA, innovative ZLD technologies, and collaborative governance. By valuing waste as a resource and embedding sustainability into economic models, the water sector can achieve resilience in the face of climate change and resource scarcity. Prioritizing stakeholder engagement and policy alignment will accelerate this paradigm shift. Part 6, Sustainability and Emerging Innovation 16. Smart technologies and automation. Smart technologies revolutionize water treatment by enhancing efficiency, reducing costs, and enabling proactive management. This section explores AI, IoT, and digital twins in modernizing water systems. 16.1 AI and machine learning for process optimization, mechanisms, predictive analytics. AI models forecast equipment failures, energy demand, and influence quality using historical and real-time data. Process control, machine learning, ML, adjusts parameters, e.g., coagulant dosage, aeration rates, dynamically to optimize treatment efficiency. Anomaly detection, neural networks identify deviations, e.g., toxic spills, membrane fouling, for rapid intervention. Applications: energy savings in aeration tanks via ML-driven dissolved oxygen control. Predictive maintenance of pumps and sensors to reduce downtime. Advantages: reduces operational costs by 10–30% through energy/chemical savings. Enhances compliance with effluent standards via adaptive control. Challenges, requires high-quality, labeled datasets for model training. Black box models may lack interpretability for operators. 16.2 Real-time monitoring with IoT sensors, mechanisms, sensor networks, deploy pH, turbidity, dew, and pressure sensors across treatment plants and distribution networks. Data transmission, IoT gateways relay data to cloud platforms, e.g., AWS IoT, Azure, for analytics. Edge computing, on-device processing for latency-sensitive actions, e.g., valve adjustments during contamination events. Applications, leak detection in pipelines via pressure anomalies. Real-time nutrient monitoring in algal bioreactors. Advantages, enables immediate response to system failures or contamination. Supports predictive maintenance and regulatory reporting. Challenges, sensor fouling in harsh environments, e.g., sewage, brine. Cybersecurity risks in connected systems. 16.3 Digital twins for treatment plant management, mechanisms, virtual replicas, physics-based or data-driven models simulate treatment processes, infrastructure, and hydraulics. Integration, combines IoT data, GIS mapping, and SCADA systems for holistic visualization. Scenario testing, evaluates impacts of storms, population growth, or process changes on system performance. Applications, optimizing chemical dosing in coagulation flocculation via real-time twin feedback. Simulating flood resilience in urban drainage networks. Advantages, reduces trial and error costs by 20–40% through virtual experimentation. Enhances operator training via immersive simulations. Challenges, high computational power and integration complexity. Model calibration requires continuous data validation. Interconnections and innovations, integrated smart systems, IoT sensors feed data into AI models, which update digital twins for real-time decision-making. Example, AI predicts a pump failure, digital twin simulates bypass options, IoT triggers valve adjustments. Emerging trends, Edge AI, deploying lightweight ML models directly on IoT devices for faster response. Blockchain, securing data integrity in decentralized water networks. 5G networks, enabling ultra-low latency communication for critical operations. Sustainability impact, reduces carbon footprint via energy-efficient automation. Extends infrastructure lifespan through predictive maintenance. Conclusion, AI, IoT, and digital twins are transforming water treatment into a data-driven, resilient industry. By embedding these technologies, utilities can achieve operational excellence, regulatory compliance, and climate adaptability. Addressing challenges, data quality, cybersecurity, and workforce upskilling will unlock the full potential of smart water systems, paving the way for sustainable, future-ready infrastructure. Part 6, Sustainability and Emerging Innovations 17. Future trends and challenges. As water scarcity and pollution intensify, innovative solutions and adaptive strategies are critical to ensure sustainable water management. This section explores emerging technologies, climate resilience, and decentralized systems shaping the future of the water sector. 17.1 Nanotechnology in water treatment, mechanisms, nanomaterials, adsorption, graphene oxide, carbon nanotubes, and metal organic frameworks, MOFs, remove heavy metals, e.g., arsenic, and micropollutants via high surface area and functional groups. Catalysis, titanium dioxide, TiO, nanoparticles degrade organic pollutants under UV light via photocatalysis. Antimicrobial agents, silver nanoparticles inactivate bacteria and viruses in membranes and filters. Nanofiltration membranes, engineered with nanopores, 110 nm, for selective removal of ions and pathogens. Applications, point-of-use filters for arsenic-contaminated groundwater in Bangladesh. Nano-enhanced membranes for PFAS removal in industrial wastewater. Advantages: ultra-high efficiency at low contaminant concentrations. Reusable nanomaterials via regeneration, e.g., pH-triggered desorption. Challenges: high production costs and scalability limitations. Potential ecotoxicity from nanoparticle release. 17.2 Climate change adaptation strategies, key approaches: resilient infrastructure, flood-proof treatment plants with elevated designs and stormwater retention basins. Drought-resistant water sources, e.g., atmospheric water harvesting, brackish groundwater desalination. Dynamic resource management, AI-driven predictive models to adjust water allocation during droughts or floods. Decentralized rainwater harvesting paired with smart grids. Ecosystem-based adaptation, restored wetlands to buffer against flooding and filter pollutants. Case studies: Netherlands Room for the River program, redesigned floodplains to protect urban water systems. Cape Town's Day Zero crisis, accelerated adoption of water reuse and demand management. Challenges: financing large-scale infrastructure upgrades. Balancing competing water demands, agriculture, industry, ecosystems. 17.3 Decentralized and modular treatment systems, mechanisms, modular units, prefabricated, containerized systems, e.g., membrane bioreactors, electrocoagulation units, for rapid deployment. Nature-based solutions, constructed wetlands for small communities. Biocar filters in rural households. Hybrid systems, solar-powered reverse osmosis, RO, paired with IoT monitoring. Applications: disaster relief, e.g., post-hurricane mobile water treatment. Remote mining camps with zero-discharge modular plants. Advantages: lower capital costs and energy use compared to centralized systems. Scalability and flexibility for fluctuating populations. Challenges: maintenance expertise in underserved areas. Regulatory hurdles for non-traditional systems. Interconnections and innovations, synergies, nanotechnology enhances decentralized systems, e.g., nanofilters in portable units. Climate adaptive designs integrate decentralized systems to reduce centralized infrastructure vulnerability. Emerging trends: bio-inspired nanomaterials, mimicking natural systems, e.g., lotus effect self-cleaning membranes. AI climate models, predicting regional water quality shifts under warming scenarios. Circular decentralization, modular systems that recover energy/nutrients, e.g., MFCs and nutrient capture. Policy and collaboration, public-private partnerships to fund modular solutions in low-income regions. Global frameworks for equitable climate adaptation, e.g., UN Water Convention. Conclusion: the future of water management hinges on integrating cutting-edge technologies, nanomaterials, AI, climate resilience, and flexible decentralized systems. While challenges like cost, scalability, and ecological risks persist, collaborative innovation and policy alignment can turn these trends into actionable solutions. Prioritizing equity, sustainability, and adaptive governance will ensure water security in an era of unprecedented environmental change. Appendices A case studies: Singapore's NE-water technology, dual membrane, microfiltration and reverse osmosis, and UV disinfection. Key features: supplies 40% of Singapore's water demand. Blends reclaimed water with reservoir supplies for indirect potable reuse. Outcomes: reduced reliance on imported water. Energy consumption: 1.5 kWh/m superscript 3. Orange County Groundwater Replenishment System, GWRS, technology, advanced oxidation, UV/HO, after microfiltration and RO. Key features: world's largest potable reuse project, 100 million gallons/day. Recharges groundwater basins to combat seawater intrusion. Outcomes: serves 850,000 residents, meets 30% of local water needs. Cost: $0.50 per cubic meter. B Key Regulatory Standards and Compliance Checklists. Regulatory Standards, EPA, USA, Clean Water Act, CWA. Effluent Guidelines for BOD, TSS, Nutrients, Safe Drinking Water Act, SDWA. Limits for arsenic, nitrate, PFAS. EU Water Framework Directive, Priority Substances, e.g., pesticides, pharmaceuticals, less than or equal to 0.1 g/L, WHO Guidelines, Reclaimed Water for Irrigation, less than or equal to 1 helminth egg/L, less than or equal to 10 E. coli/100 ml. Compliance Checklist, Design Phase, confirm contaminant-specific treatment trains, e.g., RO for PFAS. Include redundancy for critical components, pumps, sensors. Operation, monthly testing for heavy metals, pathogens, and priority pollutants. Calibrate IoT sensors and maintain logbooks. -C conversion tables and engineering formulas. Unit conversions. Parameter conversion -1 cubic meter, m superscript 3, equals 1000 liters. 1 mg/L equals 1 ppm, for dilute solutions, 1 kWh/m superscript 3 equals 3.6 mj/m superscript 3. Key formulas. 1. Organic loading rate, OLR\text kg cod/m superscript 3/day, equals \frac \text daily cod load, kg/day, \text reactor volume, m superscript 3, \2. Hydraulic retention time, HRT text hours, equals \frac text reactor volume, m superscript 3, text flow rate, m superscript 3/hour, \3. Struvite precipitation, text mg2++ text nh_4++ text po_4 3+6 text h_2 text o right arrow text mgnh_4 text po_4 .6 text h_2 text o down arrow -d. Sample designs for advanced treatment systems. Membrane bioreactor, MBR, system, components, aerobic bioreactor and submerged ultrafiltration, UF, membranes. Flux rate, 1525 L/m superscript 2/h, applications, municipal wastewater reuse, e.g., irrigation, industrial cooling. Zero liquid discharge, ZLD, plant, flow diagram, wastewater RO evaporator crystallizer. Solid salts, disposal, permeate, reuse. Key parameters, energy use, 812 kWh/m superscript 3. Recovery rate, 95-98%. References. 1. Peer-reviewed journals, Rittman, B.E., and McCarty, P.L., 2001. Environmental Biotechnology, Principles and Applications. Water Research, 35, 12, 2915 2922. Schwarzenbach, R.P., ETAL, 2006. The Challenge of Micropollutants in Aquatic Systems. Environmental Science and Technology, 40, 17, 5233-5240. 2 Industry Reports, World Bank. 2020, Wastewater, From Problem to Resource. Unwater. 2021, Global Water Security 2025, Pathways for Sustainability. 3 textbooks and manuals, Chobanoglas, G., ETAL, 2014. Wastewater Engineering, Treatment and Resource Recovery, 5th ed. McGraw-Hill, Metcalf and Eddy. Water Environment Federation, WEF. 2018, Design of Municipal Wastewater Treatment Plants, MOP8. Note, appendices provide actionable tools and references for engineers, policymakers, and researchers to implement and validate the strategies discussed in the document.